Very good afternoon, Radha here. I welcome you all for the ATAL sponsored one-week faculty development program on Internet of Things enhancing smart IoE applications using advanced processors. We are in the session 14 now. It is my privilege to introduce the speaker of today's session, Dr. Lalit Singh, sir, scientist NPCIL-BARC. Dr. Lalit Singh, sir, received his PhD degree from Indian Institute of Technology, Banaras, Hindu University. He is currently a scientist in NPCIL-BARC, Department of Atomic Energy, Government of India since 17 years and has distinction of working on pressurized heavy water reactors and light water reactors. He has an illustrious career and succeeded in several critical jobs assigned to him in his career, though each of them was challenging. His assignments over the years range from design, development, testing, related research and site validation of the safety critical computer-based systems of Indian nuclear power plants. He has published several research papers in journals of high impact factor like IEEE Transactions, IEEE Computer, ACM, ILSPAC, Quality and Reliability International, etc. He has been invited for chief guest, keynote speeches, session chairperson and talk in many international conferences, short-term courses, workshops and faculty development programs in many IITs, NITs and other institutes of national importance. He is a recipient of many awards like Publication Award, Group Achievement Award, etc. He is a reviewer of several Scopus Index journals of many reputed journals and guest lead editor of many special issues. He is supervising many PhD students of different IITs and NITs and is PhD thesis examiner of IITs and NITs and other reputed institutes. He is an expert member of Industrial Policy Formation of IIT Member, BOS of many autonomous institutes and member of the advisory board of many institutes, universities. He is a reviewer and project collaborator of research proposals of Board of Research in Nuclear Sciences. He is also faculty of Nuclear Training Program, Department of Atomic Energy, Government of India. He is interfering with other countries like Russia, USA, France, etc. for importing nuclear reactors that are based on new technologies. His research interests are in the area of reliability, safety and security of safety critical computer-based systems. So far, he has completed 33 projects of Department of Atomic Energy, Government of India. So we are privileged to have a resource person like Dr. Lalit Singh to share his knowledge in the field of IoT. Welcome you, sir. Thank you.
Thank you. Thank you, madam, for the introduction. And I would also like to thank all the organizing committee members who has given me this opportunity to share some of the research experience to all the participants. To start with, let me share my slides. So are slides visible?
Yes, sir. Yes, sir. Your screen is visible.
Yeah. Okay. Thank you, madam. So I'll be talking on reliability analysis of communication protocol for safety critical systems. So before start with the topic, let me make you understand what is the importance of this topic and what each and every terminology mean. So the first one is we need to understand the safety critical systems. So safety critical systems are those systems, the failure of which can lead to the catastrophic disasters, or it can lead to even loss of human lives. And there are various applications that are existing in the world and which are very useful in day-to-day life. For example, the aerospace, the military systems, medical domain systems, or nuclear domain systems. So these the applications which are So these kind of applications are safety critical systems because the failure of these systems can lead to very severe disasters. And hence, it is very much necessary to go for the reliability analysis of such systems. And we know like these systems are now distributed in nature also because most of the systems are remotely operated. And when the things are remotely operated, basically it is a kind of like inter-process communication. So one may be the controlling device, or one may be getting the input from other device and performing some mm, uh, calculations and then giving output to some other device. So it means the communication also plays a very important role because we need to have the correct data, and we need to ensure like the communication between the inter-processing nodes are very reliable. So reliability, if I'm talking about the reliability, it is a probability of failure-free operation of the system up to a given period of time and under certain environmental conditions. So once I said it is a probability, so it means it ranges from 0 to 1, and probability of failure free operation of the system. It means the probability of success of the system, and up to given period of time. Now that is very important. When we talk about reliability of any system, we have to talk about what period of time, up to what period of time we are talking about, because nothing is reliable for the infinite period of time, and definitely we'll have to talk with respect to like what period of time you are talking about. For example, suppose you purchase a bulb, then you get a warranty period of 1 year. Why 1 year? Why not 10 years or 20 years? Because everything is having a life, and we have to talk up to what period of time you are talking, like its reliability is this much. In fact, if you can recall your school days, you must be thinking like whoever the friends would be at that time, you would be thinking like these are he's my best friend and going to become forever. But as and when we start growing up, our priorities gets changes, our interest gets changes, and our situations gets changes. In fact, we start. It may be possible new friends start replacing our old friends. So what I mean to say is nothing is reliable for infinite period of time, and hence when I am talking about the reliability, I have to talk up to what period of time I am talking about. So I was talking. So we have seen like the essentiality of the communication systems, and definitely the communication for the communication or inter-process communication, we need to devise a protocol, and we will be talking like how we can do the reliability analysis of this communication protocol. And these are basically the concept of the Internet of Things when the different processing nodes are connecting with each other. So let us go through the today's agenda very quickly. So introduction to the reliability and background, although we have already touched upon, but we can talk with respect to the mathematical definition, so that we can the things can be easily conceptualized, and that mathematics we are going to use for our quantification of reliability purpose. Then we will discuss about a mathematical modeling technique known as Petri nets. And Petri nets is basically has been introduced to model the stochastic processes. Now, if we talk about the processes, basically it can be categorized broadly into two categories. One is the stochastic process, and second one is the deterministic process. Now, deterministic processes are those processes the outcome of which can be 100% guaranteed. For example, if I'm having a pen and if I drop that pen, I can 100% guarantee like it will definitely hit to the, or it will fall down. Why? Because of the gravitational force that is acting on it. But there are many systems. In fact, all the human-made systems are stochastic in nature, which are not deterministic in nature in the sense they contain some kind of randomness. And because of randomness, the uncertainty concept takes place, and it is required to deal with those uncertainties as well. And why these uncertainties are propagating? Because as I said, even the human being is not deterministic in nature. So definitely the creation of all the human beings will be stochastic in nature. So PatriNet was introduced in 1960s to model the stochastic processes, and because the system dynamics keeps on changing as per the dynamic situations, and hence it is a very good mathematical modeling technique where we can model the systems. And then we will also we will see like what are the various properties of the PatriNets and what are the analysis techniques. And then we will see the reliability prediction framework, in which we will be seeing like what are the various phases that are existing in this framework, and we will be probably taking a case study where we will see like how those steps can be applied on the real case study. Then we can conclude our session. Reliability, if you see mathematically, for example, X is a random variable and it represents the time to failure of a component. Means up to that much time it will not fail, and after this time it will fail. So the reliability of the component at time t will be given by Rxt. I told you like reliability is a function of time, and it is nothing but it is the probability that X must be greater than T, because I should guarantee like it should not fail before T time. So then it will be reliable. And from the total probability law, it will be equated, it can be equated as 1 minus probability X is less than is equal to T. That is, X and probability X is less than is equal to T is nothing, but it is failure probability. So reliability is equal to 1 minus failure probability, and failure probability is nothing but it is an unreliability. So if we say that reliability plus unreliability is equal to 1 from the total probability. Now let us have a look on the traditional methods which were being used for quantification of the reliability. So some of the prominent traditional methods which are still being used are one of them is the reliability block diagram. And what happens in the reliability block diagram? We try to analyze the logical architecture of the system. For example, in the system, if I talk about the architecture, it means how many components are there and what are the various interfaces and what is the overall layout of those components in the system. And those components may be arranged in a series and parallel in parallel blocks. So we can assign the reliability of each of these basic components, and then we can evaluate, or we can solve this reliability block diagram from the series and parallel formula of the reliability. For example, if I do have a system which contains only two components having reliability R1 and R2, and they are in the series, then the reliability of the overall system will be R1 into R2. And similarly, the parallel reliability formula can be used to derive the reliability where the components are in parallel. And if they are in series and parallel combinations, in similar fashion, we can solve this. So if you look, then the next method is known as reliability graph. And reliability graph is also like a reliability block diagram only. Only the basic building blocks are different. It contains nodes and arc, where nodes are used to model the link between two components, and arc is used to model the components in the system. And so if you see in this figure, the left figure represents the reliability graph, where A, B, C, D are the nodes, and V1, V2 up to V5 are the edges. So as I said, the nodes are representing basically, they represent the connectors between the components, and edge represent the component itself. So the reliability graphs can be transformed into equivalent reliability block diagram, and the equivalent reliability block diagram of this reliability graph is shown in the right side of this figure. So here we can see all the V's are the basic components from 1 to 5, and all these edges A, B, C, D are representing basically the connectors between these components. And then we can assign the reliability of these basic components, and we can use the series and parallel formula to compute the overall reliability of the system. Now the next prominent method is known as fault tree method, and which is very useful, and basically it is a kind of deductive approach. For example, suppose I say my laptop is not working. So this is the failure observation. Then I will keep on deducing the reasons. So the reasons could be power button is not on, is not getting on. This could be one reason. Electronic component failure. This could be second reason. Power supply failure. This could be third reason. So these three could be in the OR logic. Then if then I will try to deduce further. For example, if I say power button is not oning, what could be the causes? There could be mechanical problem. Either the button might have stuck, or like the contact might have damaged. So these could be the reasons. So in this way, basically, we will try to deduce further and further till we reach to the basic reason or basic event, and we can assign the failure probability of the basic event, and then we can solve. For example, if there are two basic events which are in AND logic in the sense, if I say anybody is not able to see, now the AND logic could be is left eye is not working and right eye is not working. So this is the AND logic. AND gate will be used. So when the events are arranged in the AND logic, the top probability can be calculated by multiplying these and these basic probabilities, basic failure probabilities of two events. And when they are in the OR logic, the top level probability can be failure probability can be calculated by summing up all those failure probabilities. So in this way, we can keep on computing. So law of fault tree, nothing but it is a deductive technique, and we will try to deduce reasons and try to, and it is the combination of OR and the gates where we can solve by assigning the probability of the failure probability of basic events. Now, the models that we have looked at so far are basically very good for deterministic kind of processes where already the things are known. And but as I said, the things are very much dynamic, and it depends on the dynamic scenarios, and hence a different kind of approach needs to be followed to model those dynamic systems. So, for example, different kind of approach in then there are the scientists and the researchers started deriving the various approaches, such approaches. So for one of the modeling technique is Markov model, and this has been introduced by Andrew Markov in 1940s, who was a Russian mathematician, and he said like a, any system can be decomposed into various states. We can see like we can identify the total number of states in any system. For example, if I'm talking about a human being, the states could be eating, sleeping, talking, running, and then we can find out the probability of a system being in each state, and we can sum up all the probabilities of my system being in success states. That will give the reliability, quantification of the reliability. The other way out, because the failure states are very less. For example, in the human being, these were all the behavioral states. The failure states could be meeting an accident. So if I am able to find out the probability of the system of to be in accident state, and I can from the total probability law, I can subtract that probability from 1. That will give the overall reliability of the system. So in this way, we can predict the reliability of the system. Now, so Markov models are basically has been proven to be the very powerful tools because it provides some modeling capability for all sort of dependencies. And it has a capability to depict the stochastic processes. And if we talk about the basic building blocks of these Markov chain, it contains the states and the transition probability between those states, so or on those states. So and now there is some mathematical concept. For example, if there are the two states in the Markov chain, say I and j, and the transition rate from I to j, transition rate means number of transitions per unit time, is suppose qij, then we can define the transition rate from I state to I state is equal to minus summation of all the transition rates from the same state to all other states. And now we can define one matrix, the transition matrix, or we can name it generator matrix also, where we can write the total number of states in rows and columns, and we can fill in those matrix elements by the transition rates from one state to all other states. And now the second concept, as I had discussed, is known as PatriNet. And this PatriNet concept has been introduced by C.A. Patry, who was a German PhD scholar, and he has introduced this concept in 1960s. And it is a very good visual, very good mathematical tool and graphical tool as well. Why mathematical tool? Because we can embed our mathematical knowledge in this model, and we can derive so many critical attributes mathematically, which can give more and more insights about the system. And why it is a graphical tool? Because we can represent the system behavior graphically, and all the stakeholder can have a feel like how in the real time your system is going to work. So that is this concept of a graphical tool has been very fruitful when suppose your anybody is a businessman and he is not a technology person, and he want to outsource some of the project, and he want to ensure like whether all the requirements have been taken care on. So at least all the functional requirements have been taken care on. So then what the development agency can do, he can model all the requirements, and he can show to the businessman, and where he can ensure like all the requirements have been accommodated. Because generally if you see like the software projects fail because of the ambiguity in the requirements. So it is the best communication means between theoreticians and practitioners, and we can model any kind of systems. So now let us look the history of the Patrinet, starting from the origination to the various milestone that it has achieved, due to which it has become more and more popularized. So as I said, the concept has been introduced in 1962 by C.A. Petri in his dissertation, in his PhD dissertation. He was a German PhD scholar. And the people have gone through this thesis, and then MIT USA thought of conducting a conference to evaluate this model for its applicability on the concurrent processes or the parallel computation, because that was the era where the universities or industries were striving to work on the parallel systems. And with this objective, MIT USA conducted a conference on concurrent system and parallel computation in 1970. And they have decided again to meet after a couple of years with the objective to identify what could be the related methods that can be used. And so with this objective, again in 1975, MIT USA conducted a conference on patronets and related methods. And then people started using it in the industries for at least modeling purposes, and where industries were finding difficulty to train to give the very basic knowledge. And so they were expecting like there could be some of the agencies who can start the courses on the basic modeling techniques on patronets. So that like people can be hired, and it can, and a lot of training time can be saved. With this objective, a course on general net theory of processes and system was started in 1979. And now the people started looking into like what kind of applications that can be modeled through the patronets, and they wanted to analyze basically. So with this objective in 1980, France conducted the first European workshop on applications in theory of patronets. And now then the various flavor of patronets started coming up, because people were also interested, for example, in the real-time system where the timing information plays a very important role, and the response time plays a very important role. And for that, the timed patronet where we can embed the timing information has been introduced. And other than this, there are so many other flavors of patronets have been introduced. But in 1985, Italy conducted the first international workshop on the timed patronets. So this was the history, stating only few milestones just to realize the popularity of these patronets from industries. And if you look into the patronet applications, it has a potential to cater almost all kind of applications. Now let us look about the modeling construct of these patronets. What are the basic building blocks? And we have taken a very small basic example just to understand the working mechanism also of these patronets. So, for example, I want to model a very small chemical reaction that is hydrogen plus oxygen, that gives water. And this figure that is shown is battery net figure. So first let's discuss what are the basic building blocks of this battery nets. Then we will see how this equation can be modeled using this battery net. And then we will take a case study so that we can easily understand like how the things have been modeled in the larger scale. There are the three big circles in this figure, and each big circle is known as place. So there are the three places, and I'm representing one place for hydrogen, one place for oxygen, one place for water. Then there is a rectangular bar that is known as transition. So there is a one transition T. We will see all the significance of all these building blocks. First, I'm only touching about the building blocks. What are the various building blocks? Then you can see there is an arc. There are the three arcs basically. One is connecting from the hydrogen place to transition T. So oxygen place to transition T, and from transition T to water place. And there is a weight. Now, if you are able to see, there is a numeric number that is assigned on the arc, is known as weight of that arc. So you can see the arc that is connecting hydrogen place and transition T is having weight 2. The arc that is connecting oxygen place and transition T is having weight 1, and which is connecting the transition T and water place is having weight 2. So these, for example, so where I have not put the weight, by default it is treated as 1. So you can see in this figure, the arc which is connecting oxygen place and transition T does not have any weight, so it is treated as 1. Weight is 1. Now, there is a concept of input arc and output arc. So the entity on which all the arcs are terminating, for that entity, all those arcs are known as input arc. And from where it is emitting is known as output arc. For example, if you consider the hydrogen place, the one arc is output arc, which is connecting to transition T. For oxygen place, one arc is output arc, which is connecting to transition T. For transition, there are the two input arc coming from hydrogen and oxygen, and one output arc going to water place. And for water place, there is one input arc coming from transition T. Similarly, there is a concept of input places, output places, input transitions, and output transitions. So the places which are connected from input arc or output arc are known as input or output place respectively, and similarly for the transitions. So now it is important that the arc cannot connect place to place directly or transition to transition directly. It has to be connected through place has to be connected through transition, and transitions has to be connected through place. Now, there is one more building block. If you can see in hydrogen place, there are the two embedded circles. And these embedded circles are nothing but known as tokens. So the hydrogen place is containing 2 tokens, and oxygen place is containing 2 tokens, water place is containing 0 tokens. So here, now let us understand. So this 2 token, why hydrogen? I have put 2 tokens because hydrogen contains 2 atoms. So I'm trying to represent the number of atoms of the hydrogen by tokens. Similarly, I'm trying to represent the number of atoms of oxygen, that is 2 here. Now, if you see this figure is a Petri-net figure and it represents the state of the system. It basically represents the left side of this chemical reaction. So now it has to convert into water. So how means we have to change the state. Now there is a rule how we can change the state of the Petri-net. So a Petri-net can change its state only when any transition is in enabled state. So for example, in this figure, there is only one transition. So this transition needs to be in enabled state. So for now transition can be on in enabled state when all the input places must contain sufficient number of tokens. So if you see for this transition, there are the two input places, that is hydrogen and oxygen, and these places must contain sufficient number of tokens. Who will decide the sufficiency criteria of the tokens? That will be decided by the weight of the arc that are connecting those places. So if you see the hydrogen, the weight of the arc which is connecting hydrogen place and transition T is 2. So that means hydrogen place must contain at least 2 number of tokens. Similarly, the weight of the arc which is connecting oxygen place and transition is 1. So the weight of the arc, the oxygen must contain at least 1 number of tokens. So, and it is containing 2. So it means this sufficiency criteria is applicable. Now, so T is here, T is in enabled condition. So when it is in enabled condition, it fires. And when it fires, the movement of the tokens from input places to output places occurs. And how many number of tokens will be removed from the input place, and how many will be deposited into the output place, that will totally will be governed by the weight of the input and output arcs respectively. So for example, if you see in this figure, the weight of the arc which is connecting hydrogen place and transition T is 2. So after firing of T, the 2 tokens will be moved out. And the weight of the arc that is connecting oxygen place and transition T is 1. So after firing T, the 1 token will be moved out. So on total, the 3 tokens will be moved out on after firing T. And how many tokens will be deposited into water? That will be totally governed by the weight of the output arc. So weight of the output arc is here 2. So 2 tokens will be deposited. So in the sense, although the 3 tokens has been moved out, but the 2 tokens are only depositing. So there is no law of conservation of tokens. The movement, the removal of the tokens and the deposition of the token will be totally governed by the weight of the inputs and output arcs respectively. So now the state has been changed. So 2 tokens has been moved out from hydrogen place and 1 token has been moved out from oxygen place, and 2 has been deposited in this. And so it means the distribution of the token, basically it represents the state of the system. So here if you see the distribution of the token is 2 2 0, because hydrogen was containing 2 tokens, oxygen was containing 2 tokens, and water is containing 0 token. Now after firing T, the token has been changed to 0, 1 and 2. So the state has been changed. And the distribution of the token is representing the state. Now there is a concept of reachability graph. Reachability graph is nothing, but it basically identifies what are the possible number of states of the system. For example, in this figure, the first state would be 220 because distribution of the tokens are representing the states. And then after transition T, the state will become 0, 1, 2. Now in this state, there is no, now transition T is not enabled because all the input place must contain sufficient number of tokens, and here hydrogen is not containing sufficient number of tokens. So now let us go through. So how we can let us refresh the Markov chain. For example, there are the two states as represented S1 and S2, and there is a transition probability from S1 to S2 and from S2 to S1. Then what the Markov property says that the next state will be depending only on the current state and not on the past state, which can be written mathematically like this. So suppose there is a sequence of random variable x1, x2, x3 with the Markov property that probability that my system is in state n plus 1 is x, then it will only depend on the probability of my system is in state n. So it is only depending on the previous state. Now this is left figure. In this, the left figure is known as the reachability graph. I have just taken a random example where these M1 is nothing but it is a state, we can say as marking also, and I said state is nothing but it is representing the distribution of the tokens. And suppose you do have 7 places in any Patrinet example, and the distribution of the places is like this. So for example, the first place is containing 1 token, second is containing 0 token, and so on. Then suppose T1 is enabled. After T1 the state is changing like to M2, from M2 it is changing to M4 after firing T2. It is just to show how the reachability graph can be shown, and which can be equivalently transformed into the Markov chain. So this is the state, and as I said, Markov chain contains the 2 building blocks, the states and the transition probabilities. So 1, 2, 3, 4, these are the states which are representing by M1, M2, M3, M4. And all the lambdas are basically transition of failure rates. So number of failures per unit time. So it will represent the transition probability basically from one state to another. Now let us go through the reliability prediction framework. We have already touched upon the discussed the preliminary knowledge which we are going to use in our framework. So it contains basically 3 steps. The first one is we have to create the Patrinet model, and then we have to convert it into the Markov chain. We have already seen how we can create a Patrinet model in the case of one small chemical reaction. However, we will take one case study of the communication system, and we will see how again we can create the Patrinet model. And we have also seen like how it can be converted into the Markov chain. And now the third phase is very important, that we have to apply the mathematical knowledge to compute the reliability. Before we start discussing the case study, let us go through the some of the concepts which we are going to use. Now suppose let pi it be the probability that a system is in a state I at time t, where I could be failure states or behavior states. Now, as t goes to infinity, these probabilities converge to the stationary distribution. Now, this is very important. What it means to say is, for example, you fill a glass with water. You can see like at the very initial point of time that water will be a zigzag, and after certain small time interval it can settle down. So it will take a very small time period to settle down. Now, just for the resemblance, you can, in place of glass, you take a very big container. For example, container of the size of your room, and you fill it with water completely, and then you lift it up and place somewhere. You will find that the water initially it will zigzag and it will take a very long time to settle down completely as compared to the water that took to settle down in the case of glass. So what I wanted to say is when the system is more and more complex, it takes longer time to settle down. So that is what, like, as t goes to infinity, theoretically we have assumed, like, when the time will be infinite, all the probabilities will converge to a stationary distribution. And now, which can be computed by these two for important equation. The first equation is very simple. It is nothing but it is only saying like the total probability will be always equal to 1. So the system of the probability of a system being in different states, if you sum up all those probabilities, it will come to 1 at a time. Now, second equation is very important to understand. Uh, I just wanted to visualize the second equation. Just take the same example of the big container when I said that it takes is at t time is equal to 0 when water waves were zigzagging very much, and it is trying to propagate towards settling process. And suppose after delta t, the zigzagging intensity it has become slightly lesser than our initial condition, and so the next state, for example, the initial state was S1, the next state is S2. So S2 will be depending on the previous state, that is S1, and into the transition probability from S1 to S2. So then suppose further after S1, sorry, after S2, after some time, it will reach to S3, where it will find like the water waves of little lesser intense. So again, the S3 will be depending on S2 as well as the transition probability from S2 to S3. In the similar way, suppose at nth state, the water has completely settled down. And so what will be the n plus state? N plus state will be just Sn only because it has now completely settled down. And but the formula holds the same. So what is this? The second equation is, this is the final state which is just equal to previous state, which is basically same when I'm taking like as t tends to infinity, because once it has settled down, it will remain in settled position into the transition probability, that is a p. So this is the second equation. So now let us understand the case study. We are trying to take a communication module, and the protocol works like in a very normal way, like the way we want to communicate with a friend. And suppose we lift up a phone and dial the number, and we say hello. We say hello. Then what we do, like, we have to wait for the acknowledgement. And if I don't get the acknowledgement, again I will say hello. And again I will wait for the acknowledgement. Once I get the acknowledgement, I will assume, or I will confirm like now the connection has been successful. Now, but once I'm not getting the acknowledgement after saying hello so many times, several times, then I can understand, like I understand that there is some connection failure, and I will cut the call and I can retry it. So the same communication protocol basically is implemented. So when suppose so there is an embedded unit, for example, which is sending some data, which is making some packet, and it is sending to some graphical user interface. So when embedded unit is sends a new packet, we keep a variable count and we set it to 1. And then it waits for the acknowledgement for a certain period of time, for example, T1 after sending packet. Now, if embedded unit receives the acknowledgement before T1, then packet send is successful. And we have kept one semaphore variable, and we are just changing it. It is a kind of flag that it has acknowledgement has been received. And if count is less than n and acknowledgement is not being received, the embedded unit retransmits the packet, and we have to increase the count because we have to keep the trace how many times we have attempted, and after certain defined amount of time we will terminate. So otherwise the embedded unit terminates the send process unsuccessfully, where the semaphore will not change. And if T1 time elapsed after the last data sent, then this semaphore variable will be destroyed. Now I want to model this protocol. So this is a PetriNet model. There are a couple of places. So this first place, PSR by 0, it is representing that embedded unit is ready to send the packet, and with the semaphore variable 0. Now this transition PS0, it is representing like embedded unit has sent the packet with sequence number, because we have to maintain the sequence number of the packets also with sequence number 0, and it set the retrieve count is equal to 1 by firing this transition. So here there's now there is one more thing that is important, which I have kept one place for representing like embedded unit gets a request from the data display unit to send the data. So it is working on the request, and once after it sends the packet, it has to wait for the acknowledgement, which is represented by PSW0. And then if suppose it detects the timeout of the wait, again it will send. So detection of the timeout is represented by this transition PSW0, and again the timer has been timed out. It is represented by this place PT0 N0. And if it has been timed out, it again sends the packet, and again it is waiting. This loop will keep on till how many number of times you want to try. And once the data packet has been sent, then it sends the display unit will send the acknowledgement, which is represented by this trigger TCOM1, and it is here PR1R. It represents the acknowledgement with sequence number 0 has been received, and because it was waiting for the acknowledgement, and so both of the tokens will be moved out, and again it will become to the ready conditions because the token will be deposited here, and it will be ready again to send the packet. Now, one interesting thing that you can see in this figure is left half is exactly the mirror image of the right half, because for reliability purpose we have considered the 2 embedded units, and so to implement the online testability feature, we are sending one packet from we are sending the packets alternatively from these embedded units. And suppose if it does not, if it fails after certain amount of trials, then PDSAU will represent that data send is unsuccessful and it is reported to the operator. Otherwise, it will report to the success. So this is now the next one is we'll have to this is the model that we have defined, and we can assign the delay also for each transitions, because how many, as I said, the safety critical systems are real time in nature, so it is very important to incorporate the time, because if anything is happening beyond the time, it doesn't make any sense. It will be treated as a system failure. So we can assign the transition delay based on various factors like elicitation approach, experts elicitation approach, or the experiences from the similar kind of projects, or from data analysis. And then after assigning the delay, we can use the tool which can run this PatriNet model to give the throughput of every transition. Throughput means number of firings per unit time of every transition. So these are the throughputs that we have got from this model. And then we have to see how many number of states are possible. So states are nothing but markings, and markings are represented by the distribution of the tokens. So you can see like it at the initial point of time only the two places are having tokens, and after this this transition will fire and the tokens will be moved out, one here and one here. So similarly, you can see like M0, it contains only two tokens at two places, and rest of the places are having 0 tokens. Similarly, M1, and in this way we can try to find out, try to identify the total number of states. And those states can be tangible states or vanishable states. Suppose if you don't want to put any time delay as your system, as per your system specification, that will be the vanishable states, because it will not take any time to transit from one state to another state. And then we have to make the reachability graph. We have already seen how we can make the reachability graph, and we can transform it into the Markov chain. So this is the Markov chain transformation, in which all the lambdas are representing the firing or the throughput of the transitions which we have already calculated. And we can derive the transition probabilities using these throughputs. So for that, what we have done, we have first created a generator matrix or transition rate matrix. So as I said, we can write all the number of states in rows and columns, and we have to just fill in those elements. And we have to keep one formula that the sum of all the rows must be 0. So sum of so sum of values of each row must be 0. So for example, you can go back and you can see from M0 to M1 there is a lambda 1, and so from M0 to M1 there is a lambda 1. Rest of all are 0, but the sum should be 0. Then we have to, from the transition rate from same place to same place will be minus lambda 1. And accordingly, we can fill in all the rest of the elements, and then we can compute the transition probability by, suppose I want to compute the transition probability from state I to state J. It is equal to the transition rate from state I to J, and we have to we normalize this transition rate by summing up the transition rate from I to all the other states, and except J is equal to I, because for I is equal to J, the probability transition probability will be 0. So you can see this is a derivation where all the diagonal elements are 0, and we have derived this transition probability. Now we have to just use those two equations which we were talking about, the stationary equations, these two equations. So the first one is the sum of all the probabilities must be equal to 1. So in our case study, all like M0 plus M1 plus M2 up to M9 is equal to 1. And this is the second equation which we have written like this. So these are the total states, and this at the stationary during a stationary scenario, all these will be converged. So this previous states will be the current state, and into the transition probability matrix which we have calculated here. And then we can solve these two equations to quantify all the M0s or M0, M1 up to M9, which are nothing but those are transition probability or failure probability, or the probability of the system being in that particular state. So for example, the probability of the system being in M0 is 0.6, 0.162. Similarly, we can solve those equations. And now, after that, we can go back into the Markov chain. We can see what are the failure states, because definitely, as I said, the success states are more in number. So it is always better to first identify the failure states and try to sum up all the probabilities of those failure states. So you can see like M3 and M8, there were the two failure states where the acknowledgement has not been sent and successful. So we have to just add these two probabilities and we have to subtract it by 1. That will give you the reliability. So this is nothing but the reliability of the communication module is equal to 1 minus M3 minus M8. So this is the reliability of the communication module. So that's all I wanted to tell. So we have seen like how the stochastic modeling technique plays a very important role for evaluating the various dependability metrics. Dependability is nothing but it is reliability, safety, performability, security. Specifically, we have talked about the reliability. And we can use this to identify the other attributes as well, dependability attributes as well. And especially if we are dealing with safety critical systems or some important system, for example, banking domain, where the systems are very critical with respect to economical point of view or risk point of view. These techniques gives a good confidence about the robustness or the reliability of the overall system. So that's all I wanted to share. In case of any questions, I will be happy to answer. Hello. 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 Hello.
Sir?
Yeah.
Yeah.
Madam,
Done it, right, sir?
yeah, the talk has finished, madam. Yeah.
Yeah, yes, sir. Yes, sir. Actually, I was listening.
Okay.
That's why I'm
Okay.
asking.
Okay, madam. Yeah.
Yeah, participants, do you have any clarifications regarding that communication protocol implementation for safety and reliability? If you have any question or any doubt, you can ask now. We'll discuss with the speaker now.
Last question, attendance link for ma'am. Is this session attendance for ma'am? Attendance link?
Yeah, that I will send, ma'am. Now I'm just asking any questions.
Okay.
Yeah.
Okay, ma'am. I think there are no questions.
Yeah.
So,
Yeah.
yeah. Okay.
Yeah. Thank you, Dr.
So,
Lalit
thank you.
Singh,
Yeah.
sir. Yes.
So,
For your
thank you.
technical expertise lecture in the field of that is on current demand nuclear. Actually, we are moving towards energy and reducing carbon emission. Many things we are seeing now. Actually, you have contented us with what is that we are the on-demand industrial applications using that.
Pardon, madam?
Yeah, sir, are you able to hear me?
Yeah, I'm able to listen. Yeah, please,
Yeah,
madam.
yes. Thank you, sir. Your session is
Yeah.
pleasant and informative, sir.
Yeah. Okay. Thank you. Thank you, madam, so much. And thank you, all of you, for your patience listening. Yeah.